All right, so we have a bullet fired from a rifle, and the rifle barrel length is 0.85 meters long. Let's do an energy bar graph here to actually figure out what's going on. You know, I call this elastic energy, and I don't really like calling it that. I'm going to call it E chemical from now on because that makes more sense to me. Because we're really igniting a chemical fire inside the rifle, and then what ends up happening is that all that chemical energy becomes kinetic. So what this means is we have the E chemical, and that's going to equal the E kinetic. And now the actual E chemical is going to be the work done to actually give the bullet kinetic energy. So here's the idea. We're going to have force times distance as the work done by the E chemical, or rather the work, the chemicals exploding do the work of giving the bullet kinetic energy. And so we'll say 5,500 is the force, times a distance of 0.85 meters, and that's going to equal 1/2. Now the mass of our bullet, let's be really careful, is 0.01 times v squared. And when we actually go ahead and get v, that's going to work out to being, let's actually do that calculation now. Work that out carefully. 1 second. Get into my calculator. Gosh golly. So there we go. So that's going to end up being, so 5,500 times 0.85. That's going to be a smaller little number there. So that's 4,675. And that's going to equal 0.005 times v squared. So when we actually do isolate v, that ends up giving us 967 meters per second. That's a pretty fast speed. I don't know if that's actually possible for a bullet. I think the speed of sound is 308 meters per second. So we're talking 3 times the speed of sound. I don't think it's going to move fast. That's a little much. All right, so that's problem number 6. For number 7, oh my goodness, a car is traveling at this speed. We want EK. Nothing major here. Let's just go ahead and do that calculation. So EK is going to equal 1/2 times 1,500 times 20 squared. And that's given me 290,000 joules. That seems reasonable for a very massive car going relatively quickly. Yep. So, let me double check that though. $300,000, sorry about that. 300,000 joules. Now, we have all this kinetic energy, and then what's going to happen is the brakes are going to dissipate all that energy. So let's get the coefficient of friction from this braking force. So I have EK equals E dissipated, and that E dissipated is going to be the work to slow the car down. So we're going to end up getting here 300,000 equals E dissipated, which is going to be the work done. So we have 300,000 is the force applied, which is 6,000 newtons given in the problem. So 6,000 times our distance that we're going to solve for. And so I'm getting a distance of 50 meters. Now we want the coefficient of friction from this braking force. Let's be really clear. So we've got 6,000 newtons equals mu times the normal force. Let's draw a free body diagram. This car is coming to a stop, so there's a friction force going left, a normal force going up and a weight force going down. So we know normal is Fg, and that normal force equal to Fg means that's equal to mass of the car, which is 1,500, times 10, which gives me a 15,000 Newton normal force. So now I can say 6,000. By the way, the formula I'm using here is friction is mu times N. 6,000 is mu times 15,000. And so our mu is equal to 0.4. All right. Now, if the same braking force were applied to a car moving twice the speed, what would the stopping distance be? Let's actually calculate that. So we're going to have 6,000. So work, okay, is going to be, so we're just going to say E kinetic energy equals E dissipated. And let's be clear here. We're going to stop it with this E dissipated is going to be the work done, which is the force times the distance. So we've got a 6,000 Newton force acting over a new unknown distance, and the kinetic energy is going to be 1/2 times the mass, which is 1,500. And the v, we're going to double the speed, so that's going to be 40 meters per second. So that's going to be 40 squared. So let's go ahead and work that out. When we do, we're going to end up getting a distance which I believe is going to be 4 times the original amount. I'm predicting we're going to get 200 meters, but let's just double check. So 750 times 40 squared. We're getting, yep, D is 200 meters. All right. And then the last question. We have the coefficient of friction between the box and the table is 0.2. And we're sliding with an initial speed of 3 meters per second. Let's draw the normal force and the weight force. We have the pushing force. And I don't know if the pushing force balances the friction force. I'm just going to draw it here. And so here, we want to calculate the friction force, so friction is mu times N. Let's go ahead and calculate that then. We know that Fn balances Fg because the box doesn't jump off the table nor does it sink into the ground. So we know that Fn, in this case, is going to equal m times g, that's going to be 2 kilograms times 10. That's the acceleration due to gravity because this is mg. So I'm getting 20 newtons for the friction force. And so we can get the friction force as F is 0.2 times 20, which is 4.0 newtons. Now we want the energy dissipated by the force of friction. Well, let's be clear. All our kinetic energy becomes dissipated, so we can say EK equals E dissipated. Let's calculate that. That's going to be 1/2. The box has a mass of 2. Its initial speed was 3 meters per second. And so we can actually say that this is 1/2 times 2 times 3 squared is E dis. That's going to give us 9 joules of energy. Lastly, determine the distance the box slides to come to a stop. We've got work is friction force times the distance. That's going to be the work is 9 joules equals our friction force, which we got as 4 newtons, times the distance. And so our distance is going to end up being 2.25 meters. All right, so that's question number 8. And the very last question, weight force, pushing force to the left, and then a friction force. All right, we want the acceleration of the box, so we got F, push, minus friction. Friction is always negative because it always wants to slow us down, at least in this class. And then our friction force, let's be clear, friction is mu times n. And let's be clear, the normal force, that's N is Fg because we balance vertically. So N is going to equal 2 times 10, which is 20 newtons. Again, I'm taking the mass times the gravitational strength. That's M, and that's G. So now the friction force is going to be 0.1 times 20. So I'm getting pushing force minus 2 equals 2 times A. The pushing force is 10, so 10 minus 2 equals 2A. And A is going to be 4 meters per second squared. Now the coefficient necessary to keep the box moving at constant velocity. Well, we already know the normal force is going to be 20 newtons. That we got from before. Now we know F push. So to keep it moving at constant velocity, so normal is 20. Now, the pushing force minus the friction, well, if we're at constant velocity, they balance. So pushing force minus friction equals 0. We have a 10 Newton force fighting a friction that balances. So what we end up getting is that the friction force is 10. So the mu coefficient of friction that we want to solve for, that's friction is mu times n. So that's going to be 10 is mu times 20. So mu is going to equal 0.5. All right, so that's it for the practice test. I'm actually going to put these videos. Vector components. Whoops. These, let's just be really clear. To get force components, don't even overthink it. We're going to have 30 times the sine of 40 here, and 30 times the cosine of 40 here. And I'll actually let you put those in your calculator. So that's how those will work. All right. So that's the last little bit of the practice test.